have any questions, please shout loudly. And I really welcome questions. It's an interesting topic, obviously, and I'm sure there will be some. So, yeah, before I start, let me just say maybe a few words. It's kind of an interesting story for me and mostly Dries. So you see my pointer, right? So these cells, there were a bunch of people involved in this work, but mostly I don't know if I should word struggling, fighting with everyone with Dries, and he did most contributions together. So we never worked on many-body localization, but we were thinking a lot about how chaos emerges, and I will briefly talk about this work led by Mahit, who was a student at the time. Also, this was involved. And then I will tell you a little bit about sort of how situation with many-body localization developed. So we decided to use our ideas to test what's going on, and then we came to conclusions that it's likely not there. It's also an very interesting experience, I should say, from the point of view of psychology, sociology. I will mention a few of the examples, but of course won't go into details. So let me just say a couple of things. So there was a friendly advice to Lev Widmer, whose work I will mention later, that it's unhealthy to question established theories. And there were actually much less friendly advices to Dries to stop quitting, to stop working on this field and quick and so on. Anyway, so I learned a lot about our community. So I will sort of the idea, or at least how I will try to structure the talk is the following. So first I will tell a little bit about like general chaos and ergodicity, starting from classical systems. I assume like most of you really know this stuff very well, but I'm not, maybe there are like newcomers, so I will summarize what's going on. And then I will slowly move to MBL. So in classical systems, chaos is usually defined as sensitivity of trajectories to small perturbations. And ergodicity is loosely again defined as if we do time average over trajectory, we will get the same answer as ensemble average. And these are like snapshots of what's going on if you take, say, two-dimensional oscillator, introduce some nonlinearity. So I usually show this to students when I teach quantum and statistical mechanics. And then if nonlinearity is small, so it's hard to see, but here epsilon is 0.5, we actually see pretty stable trajectory. So it just keeps moving and it doesn't thermalize and basically lasts for as long as you can run the simulation. And if you increase nonlinearity, so here it's 4, then you see they're actually not one, there are 2 trajectories which start nearby and they become completely random. And if we average over time, these trajectories, then we will get like perfect microcanonical ensemble. Good. So, and it was realized like a long time ago that if you talk about low dimensional single particle classical physics, ergodicity emerges slowly. Chaos emerges basically right away. So, and the more famous example is a kick trotter, where we switch on and off gravitational field, also a classical particle. It's now one-dimensional. We remove energy conservation. And then this is like a picture which probably many of you saw. It's everywhere now from Schoolopedia, which shows phase space portrait of such a kick trotter. And if nonlinearity is small, we see like very nice trajectories. Basically a Hamiltonian is time average Hamiltonian, so it's particle in some gravitational field. So we see sort of oscillations and we see like, I don't know, these big rotations. And then if we increase peak amplitude, then we see more and more chaotic motion. Just want to emphasize that chaos you can see right away, even when kick amplitude is small. You already see signatures of chaos. It's kind of noisy. So there are more signatures of chaos here, and eventually, only when nonlinearity is big, we have ergodicity. So the system explores the whole space. And there is like mathematical theory behind this called Kolmogorov-Arnold-Moser theorem, which tells us that basically small perturbations in this classical systems, they don't destroy invariant torque. And in more modern language, we basically are saying that we have dressed local, well, local is not relevant to this, but will be relevant for many particle systems. So we have dressed integrals of motion. For example, in this case, we'll have dressed energy, which is also known as Floki energy. In the previous example, we'll have dressed angular momentum. So just something connected to it. Good. Now, in quantum chaos, conventional, I would say, accepted definition is emergence of random matrix statistics. There are two powerful conjectures. There is a very Taber conjecture in 77, which basically says that if we take generic integrable systems, generic basically means that we don't have commensurate spectrum. So like the example of non-generic system is Kepler problem. So we have period of radial motion is commensurate with period of angular motion. But if we, instead of 1 over r potential, we'll have anything else like 1 over like Yukawa potential, something, it will be generic. So, and they said that in these generic integrable systems, we'll get Poisson statistics, and actually Berry himself, and then late in 1984, Bachigas et al. Formulated the conjecture for chaotic systems that will have random matrix statistics. So, and this is an example from already quite an old review. So if you take incommensurate rectangular box where sides differ by some irrational number, we'll get like very nice Poisson statistics of energy levels, no, energy gaps, I should say. And if we look into Sinai Billiard, it's the plot from original 84 paper, and study what level statistics are doing, then we will get this orthogonal ensemble from random matrix theory. And well, later numerics got better, and then now no one really questions this conjecture. I think we get like numerically perfect random matrix ensembles. So I'm not sure there is like KM theory formulated for quantum systems, at least I never heard, but it's clear that in these systems, it should work because quantum chaos is usually defined as an asymptotic statement. So when Hilbert space dimension goes to infinity, right? Because if you have 2 by 2 matrix, we cannot even say it's chaotic or not, it's just 2 by 2 matrix. So, and in these systems, we get this asymptotic regime when we approach also classical regime, right? Because if Hilbert space size gets bigger, it sort of means H bar gets smaller, energy gets bigger, and then we approach in classical regime. And in classical systems, there is KM theorem, so by continuity, it should be for quantum systems as well. So, and this conjecture was, well, later, when I would say 8-10 years, was essentially generalized to many particle systems. And there it was formulated sort of more rigorously, more precisely, I should say. It's still a conjecture. Under the name of Eigenstate thermalization hypothesis. So it's like key people were George Deutsch, Mark Svednicki, and then there was beautiful numerical work by Marcos Rigol, Vanya Dunque, and Maxim Alshani. So I'm not showing the original numerics, I'm showing numerics from Leo Santos groups. So it's basically if you take a Heisenberg model, which is known to be integrable, so this is some spins interact, well, it's XXZ model. Anyway, so it's integrable, so there's a near neighbor spins. And then we add a perturbation, which is longitudinal magnetic field. It's enough to add it on one side. We very rapidly cross over from Poisson statistics when this perturbation is 0. It's actually not exactly Poisson, but close to Poisson. And then it goes to basically Wigner-Dyson statistics when perturbation gets bigger. And again, beta numerics show that it works better in beta. So this random matrix sort of theory works well in many particle systems. And here I just want to highlight, we approach chaos not by approaching classical limit, but by taking thermodynamic limit. So basically we can understand this conjectures that if we increase number of spins in this case, of course, our matrix gets bigger and bigger, and we asymptotically approach Wigner-Dyson statistics. All right, so now let me say like one important statement, which is usually not emphasized. Actually, level statistics is not a measure of chaos. Even though it's used as definition of chaos, it's not. It's really a measure of ergodicity. So one way to understand it is that eigenstates are about time averaging, right? So it's like when we teach, quantum mechanics and explain why eigenstates are important, we usually say, well, let's take I don't know, some observable, look into long time average, and then we'll see it's a statistical mixture of stationary states. So that's why they only survive in long time limit, right? So also, more accurately, this ETH is really about ergodicity. So it just tells us because eigenstates of complex systems are like microcanonical ensembles, so in long time limit, our generic systems behave as statistical systems. So in this example, like, Sinai billiard, these two coincide. But if we imagine two disconnected Sinai billiards, so this system has to be chaotic, right? I mean, if one billiard is chaotic, two have to be chaotic. But now level statistics will not work because we have independent levels from left box and right box, and they will start crossing. So we'll get like Poisson type statistics and so on. I mean, of course, people understand it, so they want to remove symmetries and so on. But I want to say that this like trivial point was one of these issues where like MBL community was a bit confused and got like basically wrong analysis. So I'll come back. This is a very, very interesting point. And interesting it was so missed. So but anyway, in thermodynamic limit, usually chaos implies ergodicity, so this measure is fine. But then we thought, like before even moving to MBL, is there a good measure of quantum chaos, really, if you want to define chaos? So there were some proposals on out of time order correlation functions. So I don't want to go into this detail. So let me just say, those don't work for local models. There were also actually first numerical work by Boris Fine in 2015, and then there was more careful work by Tomasz Prazen group showing that in local models, OTOC are actually polynomial. It is actually still, I think, unsolved. It's not really understood like completely why there is a difference between quantum and classical systems. Anyway, so but what we thought in like 2019, 2020 in a work led by Mahit is that, well, maybe we can use sensitivity of eigenstates to define chaos. It's interesting. I just told you that eigenstates is about long time average, so sensitivity, so it's like ergodicity. And now I'm kind of contradicting myself. I'm saying, well, let's define sensitivity of eigenstates as a measure of chaos. But I'll come back to this later. This sensitivity of eigenstates is not a static response. So it's like it's sort of a diabatic response, it's a dynamic response. So we need dynamics to compute this quantity. So and sensitivity is expressed in what is known as fidelity susceptibility or Fubini study metric or whatever. It's basically overlap of derivative of wave functions, here stationary states, with respect to small perturbation. So imagine we take our Hamiltonian, say particle in a cavity, change it a little bit, Hamiltonian, and see how rapidly eigenstate changes. And then, of course, intuitively, if the system is non-chaotic, it will change a little bit. If the system is chaotic, it should change a lot. And this indeed worked. So I will not go into details of this work because I won't have time to MBL. So let me just give a summary. So we found like some, I would say, very surprising results. So indeed, Chi is a very sensitive probe of chaos. And in generic, I would say, ETH systems, so ergodic systems, it's actually very easy to show from ETH and also verify numerically that chi diverges exponentially with system size. It behaves as exponent of the entropy. I'll again come back later and I'll say where this result comes from, but it just comes from perturbation theory and ETH, nothing else. Then if we talk about integrable systems, this was not completely clear, I would say, to us and to anyone else. So what we found that chi is actually at most polynomial in the system size. So it could be a constant, or it could be like L some power, but it's never exponential. And I come back to it. So this is the way integrable systems found a way to fight small denominator problem. So small chi actually means there is no matrix elements or small energy differences. I'll come back to it. But then we found a very interesting result, which we never expected, but which is like completely generic, and we understand it now. I'll also show some numerics actually in the next slide, that there is no direct transition from integrable to ETH. And this actually just, again, I won't go into those details, but this was missed completely by all RG treatments of MBL. So if you look at them, they missed it, and well, basically they're all incorrect. So, so instead, there is like in this intermediate, I would say maximally chaotic regime in between, where chi saturates its upper bound. So you can just show e power to s is maximum. It's basically when you start moving all the spectral weight to energies of the order of level spacing, energy differences of the order of level spacing. And this is completely universal. Let me just illustrate how it works in a model. So there was a next work led by Tyler LeBlanc and Marcus Rigel group. So we tried to test what's going on in XXZ chain. So just to guide you what's plotted. So this is chi times e to the minus s. So the way we decided to plot it in this way, so that in ETH regime, this is a constant. So horizontal axis is basically integrability breaking strengths. So it's local magnetic field, but we also checked that you can have second nearest neighbors and so on. So, and you see it's logarithmic scale. It starts at very, very small numbers and goes all the way to large numbers. So basically you see in different colors the different system sizes. So red is largest, purple is smallest. So what you see is that in this intermediate regime, everything collapses. So this is ETH scaling. This is ergodic regime. When interaction becomes too large, you go to another trivial integrable regime. Interactions are so strong that system is again localized by interaction. So let me not even comment. So it's really trivial, so I don't want to go into this details. So we have ergodic regime. But then we see if the system, at any system size, at some point, we sort of peel off some ergodic curve, and then this chi starts decreasing. But it's clearly at the maximum, chi diverges like very fast. So system size changes linearly and chi changes exponentially. So this is like really exponential divergence. And if you fit it, the peak position versus integrability breaking perturbation, versus omega h, in this case, Heisenberg frequency, you'll see it's 1 over Heisenberg level spacing squared, so e power to s. And also the other thing you can see is that this point really drifts linearly with system size, but this is log scale. So we found also, I would say, unexpected result that you really need exponentially tiny perturbation, it is in this generic system, to induce chaos, or ergodicity, I should say, induce ergodicity, right? So this is the point where sort of we become a TH. So it's basically the statement that if you have a free gas in this room and we ask like, what's the interaction strengths we need to for the system to be ergodic? And it turns out exponential in system size. I would say it's a very surprising result. So it's not just one spin is enough, a magnetic field of one spin is enough to make universe ergodic, but you need exponentially small magnetic field in the universe size to make it ergodic. Of course, it will take exponentially long time, but it's interesting how little you need for ergodicity. So, and then we checked, this is close already to MBL, what happens in Anderson insulator. So now we have basically free electrons with disorder, and then we had small interaction. So here, all the parameters of the order of 1. This is not like standard MBL regime. And system size a little bit smaller because we don't have momentum conservation. And once we checked it, actually the same story. So we still see a same maximum, which scales as e power to s, and we see even exponential drift of integrability perturbation to 0 with system size. So in this sense, it's kind of already a warning sign. I mean, people somehow like claimed and thought that Anderson insulator should be stable to interactions. It's not the case. Okay, so now let me go to MBL. And then, again, I will give some overview of what's going on, and then I will basically show some brief history in some papers. I apologize, I will mention only limited class of papers, and I saw Jessica is here, and I apologize, I'm not mentioning your work, just for the sake of time, because there are too many. So basically, let me give like first an overview of what people thought MBL phase is and how it works. So originally, it was mentioned as a possibility, I think, by Anderson, and by some other people, but it's sort of formalized more in this 2005-2006 papers. And there is Anzager Prize for this next year. So the idea is that, well, MBL is roughly a localization in Fock space. So system is interacting. So we can think about sites as sort of a hypercube lattice where, say, ones and zeros mean that on a given site there is a particle and there is no particle. So for example, if one particle hops from one side to another, I go from this side of hypercubic lattice to this side of hypercubic lattice. And then sort of the idea, so this is, I stole from Zlatko Pavić's talk, that we have like three possibilities or two main possibilities. So one where the phase is delocalized. If we look into Eigenstate, it kind of spans all the sites in this hypercube lattice. Of course, consistent with energy conservation, but anyway, so basically all sites. So it's ergodic system. So, and then in the localized regime, actually the idea the system is localized. So it's only a particle just moves a little bit virtually and then comes back. So we got a little bit of dressing of particle, but it doesn't spread. So, and the idea why many body localizations happens is that we have a competition between exponentially growing density of states, right? It's a hypercube. So if we start doing hops, we connect to like exponentially more and more sites, right? But on the other hand, the matrix elements were argued to reduce exponentially. So it's one exponent versus another exponent. And if disorder is sufficiently big, this reduction is stronger and the system is localized. So basically, in some sense, matrix elements should decay faster than density of states. So, and then, of course, people wanted to check it numerically, and later I'll mention experimentally. And luckily, I would say, for us, there was pretty much a standard model for MBL where most of numerics has been done. There were other models which were studied, but this is considered to be like standard, I should say. So it's a disordered Heisenberg chain. So we have, well, sometimes people consider XXZ chain. It's basically the same. So we have this basically system which I introduced before. So we have isotropic spin-spin interaction. And then on each side, we get a disordered magnetic field. So in terms of particles, this is like disordered chemical potential. And this spin-spin interactions encode nearest neighbor interactions and hopping. So you can formulate this problem as problem of interacting fermions. So, and then there were many numerical works, and I will, as I said, really mention subset of it. I don't want to offend anyone. I just took some most cited papers. So So the probe of MBL was initially, which people used, was the same I mentioned in the beginning, this random matrix statistics. But it's hard to really look into distribution functions. So people use so-called ratio. So it's sort of ratio.
Sorry, this is like security checks, but
Yeah,
fine.
don't worry. So it's basically a ratio of nearby level spacings, like n to n plus 1 and n plus 1 to n plus 2. And you can compute like average of this ratio. And there are different numbers for Poisson statistics and Wigner-Dyson. So for GOE, it's a particular number, which is 0.53. And for Poisson, it's some other number, I forgot, 0.39 or something. And then you can just basically plot this number versus, say, disorder and see how this number changes. Right, and then this was done for this model, and then you just see, like, I know there are bigger system sizes, and they are sort of drifting here on the right. But then there is like a nice crossing point at disorder roughly 3.6, 3.7, and then there was even like scaling collapse near this disorder. It's not perfect, but looks fairly good. And so they concluded that there is a critical disorder where beyond which the system is basically localized, even the thermodynamic limit. So this drift will stop, and then at the end, everything will cross here. So, and by the way, this is like a very, very important result because it tells us that there is a system where KM theory works in thermodynamic limit. It's quantum, it's not classical, but this is basically KM. So this MBL can be understood as existence of this local integrals of motion, basically dressed magnetization. It's a big result. And then there is another example from the paper by Maxim Serbin and others who looked into a different measure, but is also tied to random matrix theory. It's basically a ratio of matrix element between nearby levels over energy difference. And then the idea that if the system is ETH, well, this is from ETH exponent e to the minus s over 2. This is e to the minus s. So this should increase. But if the system is localized, this matrix elements are small because basically we have disconnected boxes and nearby levels, they come from totally different boxes, right? So even though denominator is small, this is even smaller. And indeed, they saw something like this. So when disorder is 0.5, so it's ergodic, as they increase system size, the peak of the whole distribution of this G and average, of course, drifts to the right. So as I said, the larger the system, the bigger this ratio. So at disorder 3.6, it roughly doesn't move. I mean, it gets a bit broader, but it doesn't move. And when disorder is like 5, we're deep in the MBL phase, the ratio drifts to the left. So we have larger, if you increase system size, we basically have, well, our matrix elements on average get smaller and smaller in units of this energy difference. Okay, and as I said, there are many other papers confirming this MBL transition near 3.6. There was an analytic proof of stability by Joe Imbri with some extra assumptions like level attractions, which showed that this local integrals of motion are stable. There was also beautiful experimental confirmation called atoms in a group of Emmanuel Bloch. Probably most of you saw this picture. So they prepared what's known as charge density wave state in quasi-periodic potential. It's not disordered, but it has like 2 waves with different period, and it's believed and numerically behaves in almost the same way. So, and then they let the particles relax. So if the system is ergodic, then density should be uniform. And if it's localized, we should still have memory. We should have charge density wave. And they plot imbalance as a function of time for different interactions and different disorder. And the point is they see that even when interactions are like non-zero, if there is sufficiently big disorder, it looks like it's localizes. And in beta numerics, this decay is even smaller. So it looks like there is localization. So basically, by 2018, the situation is largely clear. Only details are missing, like what's the correct critical exponents? So are G schemes predicted Korsellitz-Taulis? What are subdiffusion exponents and so on? So basically, field is closed. So, but people were trying still to get like, better, better understanding of these details and so on. And then interesting events started to emerge. So there is a paper like in 2018. So people got better numerics. There is a paper in Karlsruhe group in 2018 where they basically looked in the same imbalance. So this paper by Manuel Bloch was very influential. So that's what many started studying numerically. And they looked at the imbalance in basically infinite system size, but finite time. So this is some Krylov's methods. I'm not really sure in details. And they actually found that where transition sought before, the system decays, but slowly. So they gave now a low bound for the transition, like 5.5, 5.7. And I just want to mention, and I will highlight it later, it's not just a mere small change in disorder. Like relevant scales are like time scales. They're exponential in disorder. So this factor of, 60% in disorder means like, 3 orders of magnitude in time. So it's really like a big thing. And they said that, well, if they have like higher confidence, like for sigma, they can rule out any transition for disorder below 5. I mean, this paper was largely unnoticed, but nevertheless, it's appeared. And then in 2019, there was like, it was a revolution. So I will show results from this paper by Suntaj et al. It's basically in Ljubljana group. So, and I spoke, I wasn't actually thesis defense in Amsterdam when I saw Tomasz was also in the committee, and it was just before results were published, like 1 month before. He showed privately to a group of people, including myself. And he even said that they decided to use spectral form factor. It's sort of a Naja measure from random matrix theory to find better where the transition is. And then they tried hard and so on, and then they concluded that, well, maybe there is no transition. So maybe the king actually has no clauses. So these are the results from that work. So they computed ratio of Heisenberg time, which is inverse level spacing, and Taulis time. This is like at a time where they see random matrix statistics. And it's basically using expectation value of this z squared, like spectral form factor. And then when they plot this G versus disorder, they see like, some like featureless things. So the bigger system size, everything drifts. But if they try to plot the same ratio versus W over L, they actually see a very good crossing point. So from this numerics, it looks like transition is consistent with critical disorder flowing over law. And I have to say, there was immediate critique of this work. So they were saying, well, but this disorder, you see numbers, it's much less than 3.5 and 6. So this is all an ergodic regime. And then there were statements that, they really don't know how to do finite size scaling. This is all like, real trivial finite size effects and so on. So this paper was criticized a lot. But nevertheless, they kept working, and then they said, well, let's try to do like best scaling collapse without assuming where a critical point is. So we will say, well, maybe critical point depends on L, right? So there is, of course, transition. No one questions. It's just the question whether it happens at finite disorder or a disorder which changes with L. So they said, well, let's just find best scaling collapse, assuming WC is some function of L, right? And then they found that there is a very good collapse, which is indeed like, of course, Korsellitz-Taulis type, which happens near this maximum. So previous attempts of collapse were here, and they violated Harry's bounds and so on. So here collapse looks much better. And this sort of blind numerical procedure tells you that if there is a transition, it's here. And here it's obviously drifts. Like there is no question. This was actually our motivation to enter it. I told you I started the talk from fidelity susceptibility. So we decided after we learned about this paper by Suntats by Ljubljana group, we decided to check what's going on. And then we looked into fidelity susceptibility in the same model. And then this insert shows the Bear graph plot, like how fidelity susceptibility again changes with disorder for different system sizes, and it's clearly drifts. Actually, this, if you plot it in log scale, you just see it linearly drifts. And what we got is completely consistent with what Prezan and others got. And if we scale it by E power entropy, then we have like perfect ETH collapse, and we see drift here. We thought again a bit about this crossing point, but then we concluded it's again spurious because it's clear from this. So if there is a crossing point, it should be not scale susceptibility. So and then we extracted, maybe in the end of the talk, I have a few minutes, I'm not sure. The tau is time, basically when the system should go to diffusive regime from this, and we got like same results as Ljubljana group got from spectral form factor. It's like exponential in disorder with some number 3.5 roughly, and I will mention later why this is important. Anyway, so it looks like it drifts. But we got the same critique as these guys that, well, disorder is too small and so on. But people started like checking, like they started to be more careful. They decided, okay, well, let's try to check more carefully where the transition point was. And then there is a paper from 2020 by Piotr Siran, Zakrevsky, and Levenstein. So they tried to extract WC from entanglement entropy. Actually, again, had different probes. So one, they looked into when this entropy is like 0.8 of thermal value, and they found indeed this grows linearly. So this is sort of plotted as 1/L, so it's like this. But they also looked into a point where difference between entanglement entropies of systems L-1 and L+1 becomes 0. So when they're same, and they extracted a different disorder which behaves sort of linearly with 1/L, it's more like kind of a finite size effect. And they argued that when these lines cross, that's where we really have a transition. They have slightly different lines. And then they again concluded that critical disorder should be around 5.3. So this is consistent with Gordon. So, okay, I mean, transition is a little bit higher, so maybe it's not a big deal. But then in next year, it's actually already this year, we are talking about 21, more papers appeared. So the one by Vedic and David Hughes and Alan Morningstar, I'll show you shortly, they said that, well, let's just try to study slowest operator. So the motivation was that let's consider an open system where, say, last spin is coupled to a boundary spin. So they basically study limbled dynamics. And then they asked, what's the slowest mode of this system? And the idea, the slowest mode, the slowest operator in the system, the slowest operator is basically L bit localized on this side, right? Because it's least connected to the boundary. So mathematically, this problem amounts to finding smallest commutator of this boundary of this slowest operator with any boundary spin, it can be X, Y, Z, and asking how this operator, norm of this operator decays with the system size. If the system is localized, it should decay exponentially, right? Because if I make system bigger and bigger, then my operator can sit further and further from the boundary and basically can live forever. And there were arguments that it should decay at least as 4 power L There were some avalanche arguments. I'm not going into details, but basically they were checking this thing. And then, well, it's an open system, so they were working with small system sizes up to 9. It's a Hilbert space. And then essentially, this is like 4 power L, which I sort of briefly mentioned, times medium of this decay rate, 1 over tau. And then they see, well, these things should basically, if the system is bigger, it should decay very quickly at large disorder, and conversely, it should increase because of this 4 power L if disorder is small. So again, they see crossing point, well, it's clearly drifts, and these values get bigger and bigger. So they concluded, well, if there is a transition, it should be above disorder 7, right? Remember, 10 years was 3.6. Well, same year, 2021, so these people from Poland, Sirant and Zakrevsky, they looked into imbalance decay, and now they had even better numerics. So this is imbalance, this is disorder 8, and this are different system sizes. And they found, you see, the range is very small, but they found like actually there is very persistent drift downwards. So it's logarithmic at time, it's very, very slow, but it's there. And they concluded that there cannot be any transition for W less than 10. It decays, it's just very slow. Yeah, I apologize, I didn't include papers by Jasko, so he was in parallel doing similar numerics, and he saw like log and time decay, but he also came to the same conclusion that systems decay. So now tau less time in the ergodic phase, remember it's 3.5 times W, at least e power 35. This is the minimal time even to CMBL transition, because at W10 there is no transition. If something happens to time, it can only slow down. So, and at this point it becomes almost unimportant which units we are using. So then in actually the same 2021, Dries realized that he can find a clever trick to reduce complexity of the problem of finding slowest operator from Hilbert space dimension squared to Hilbert space dimension. And he essentially extended results to larger system sizes from 9 to 14. And then it's the same quantity, it's this decay rate times 4 power L. Again, if system is MBL, this should really decay very fast with system size, because gamma should decay exponentially fast with system size with exponent controlled by W, not by whatever 4. And then if system is ergodic, then gamma is roughly constant and 4 power L dominates. So this is ergodic system, this is exponentially grows. But then you see, now we're talking about disorder, which is like deep in MBL phase. You see, it's actually, well, maybe at largest disorder it decays, but then it's clearly turns around. So, and Dries concluded that you cannot have transition for disorder less than 22. It means that time of the universe is not enough to observe transition. So this transition, even if it's there, well, of course, there is no sign of the transition, but imagine the W100 there is transition. That's what now some MBL people say. Well, but then it's already unobservable, because already e power 70, use any units, nanoseconds, seconds, milliseconds, it's time which is like beyond time of the universe. So, and it's unobservable, number one. Then every single numerical extrapolation of WC was wrong, right? So, and it's actually very interesting. You come back to these papers and you see it's like indeed wishful thinking. So there is a straight line over a line which bends and so on. Even in those numerics I showed to you, you can actually see that you cannot draw straight lines through curves which are really bending. Like here, for example, if you wouldn't multiply by 4 power L, of course you add additional slope. And then on the slope, this curvature is barely visible. But if you look carefully, if you do careful finite size analysis, of course, you will see that these lines are not straight. So there is no exponential decay of L bits and so on. So, and all key discovered features of the MBL phase, like log T entanglement growth and so on, were actually observed in ergodic parameter regime. It's like what was thought deep in MBL phase is now understood that it's like basically transient finite size system. I'll come back to it. It's basically glassy phase. So that's the status. So, and now in the last, I don't know, 10, 15 minutes, let me briefly explain what we think is going on. And yeah. So we kept thinking about this with Dries, and then we actually came up, understood that you can understand like sort of most of physics from a very simple model. So let's consider an impurity spin, how we call it, like basically spin which is coupled to a chain via weak link. And actually, it could be either in the middle or in the edge. I just produced one picture. You'll see in sort of plots what is going on. So right now, let's consider this system to be ergodic. So we have one spin. So basically, large disorder on one side. It's a really trivial system. So our Hamiltonian is H bus plus some large V times S on boundary plus a coupling, generic coupling of this impurity with the bus. And I will use like epsilon, this small parameter to justify FGR and so on. But I mean, numerically, it can be of the order of 1. Just it's an expansion parameter. And then we looked numerically what happens with this level ratio. And then first, let's look into solid lines. So here, impurity is in the middle. So this is like a cartoon. So it's not this graph, but imagine there is a copy of the system on the right. So the purity is in the middle. And then this solid lines is what happens with this R ratio. So this is, of course, bigger and bigger system size. Its largest is 18, I think. So we see that, yeah, there is this Wigner-Dyson statistics, peak drifts. Values are roughly the same as MBL, like slightly bigger, but same scale, same behavior. And then there are also dashed lines. And dashed lines are what we call an effective model. It's where we freeze this impurity, do Schrieffer-Wolff transformation, and then we basically get J squared over 2V coupling. But now we have two sectors for the Schrieffer-Wolff, up and down, right? And then solid lines are basically where we superimpose this model and this model with correct energy shift. So this, remember, I started from these two boxes. So these are exactly these two boxes. So we have one box corresponding to impurity spin up and one box corresponding to impurity spin down. Then you see the solid lines for large V like very well agree with exact numerics. So this sort of cartoon gives you very good description. So what we learn from this? Well, first we learned that at V of the order of L, or more precisely L over log L, I'll come back to this later, impurity freezes. So roughly when V is so big, there is not enough energy in the bus so that impurity can relax. But there is another scale, which is much bigger. And this is the scale where each box actually disconnected to two boxes. So, and this is related to what I mentioned in the beginning. If you have an ergodic system, we need exponentially small perturbation in the system size to induce ergodicity. So it's roughly here for this model, we know it's like it's e power entropy over 2. So when this happens, when V is bigger than this, it means J squared over V is smaller than this e to the minus S over 2. We really have 4 disconnected blocks, right? One spin up, one spin down, one left, one right. So we have 4 disconnected systems. But when V is larger than L and smaller than e power L, we actually have this strange non-perturbative, non-ergodic regime. So there is no Poisson statistics and so on. No Wigner-Dyson statistics. I mean, one thing you can see that here we don't go to Poisson statistics, and we can say, oh, that's not the same as MBL. But the reason is actually trivial. So here, up and down box, they separated by energy V, which is over the order of L. So basically, these levels simply don't overlap. And that's the reason why we will see Poisson statistics only at this exponentially big L when each block will separate. Otherwise, we have really two ergodic blocks, up ergodic and down ergodic. So, and then we can look into fidelity susceptibility. And these are the same plots I showed in the beginning. This is full model. And then we see the peak drifts, and it drifts linearly with L. There is no way for small system sizes you can extract log L. And then if you look into effective weak link model, then we actually see same thing, but now peak drifts exponentially with system size. So it's consistent with this E to S over 2. So, but look, scales are the same. So even though one is linear, one is exponential, it's still disorder 3 and 4. So this was also like one of the reasons it was hard to disentangle things. We need to much bigger system sizes to really see good separation between exponential and polynomial. Like otherwise we have exponential 3 and polynomial 3. Now, let me go to more impurities. So now it's sort of the same story. If we have full model, we again have the same drifts. Now numbers a little bit smaller, but not much. And then we see that, well, now full model shows two things. This curves become steeper. Well, because we have more boxes, we have better Poisson statistics, right? We have, this is like one box corresponds to all impurities, say up, another box, 2 up, 1 down, and so on. We have 2 power number of impurity boxes, right? So of course we'll get better Poisson statistics if we have more and more boxes. It's clear, and that's what's going on. So this part drifts. For green line, which is full model, we actually don't have full line because system size is a bit too big. So for effective model, we can do it because these impurities are substituted by weak links and system size is small, but full we can. But look what happens. So this departure from the solid line moves to the left, this moves to the right. So if you plot it, we will get very good crossing point. And in some other like situations with smaller blocks, we got it. So there is a perfect crossing point, which people took for MBL transition. And it's completely meaningless. It has zero meaning whatsoever. Because now in this model, we can look into just one effective block. And you see now the crossing point is much to the right, and it drifts like very fast. It drifts exponentially. So, and this means that we actually have a collection of ergodic systems, right, corresponding to up, down, up, down. And of course, if we keep system size, increase system size and don't increase disorder, we will normalize because each of them is like ergodic bath. It will melt any of the impurities. Okay, so now how can we understand this more quantitatively? I have like 2 more slides. I hope I'll finish in 7 minutes. I started 5 minutes late. So I hope it's okay.
It's fine. Thanks.
So, well, we can go to the rotating frame with respect to this impurity, right? And then we eliminate impurity potential because we go into rotating frame. But now our links, so our spin basically starts rotating in XY plane with frequency V. We use a potential. So it means that our coupling to the bath is basically modulated with V. And this is a Floquet problem. And actually, there was like interest to studying this problem from operator growth perspective. So it's also, people looked into quantum chaos from this point of view. And there were results, recent showing that if we look into a spectral function, which is the same as Fermi golden rule rate at frequency omega, then it behaves as essentially exponent, and in one dimension there is omega log omega. There were a bit earlier works by Dima Abanian and Takashi Mori who got this bound without log omega, but then corrected. So this log omega exactly what leads to log L, which I mentioned. So, and it kind of makes sense. So we want to dump a large energy to the system, right? But we have finite bandwidth. So we really need to go to non-perturbative, I don't know, in frequency results to understand like Fermi-Golden rule 8. And yeah, there were a bunch of papers asserting this. And then we can understand in this system, well, there is a simple criterion for localization, which is maybe not necessary, but sufficient. So when this gamma becomes of the order of level spacing, of course, the system local, right? Because, I mean, if Fermi-Golden rule rate is less than level spacing, we cannot use Fermi-Golden rule rate. It will stop. We'll get Rabi oscillations instead. So, and this immediately gives, well, our frequency is V, right? Because we are in the rotating rate oscillate with V. It gives us immediately this critical disorder, which I mentioned. It's basically L over log L. So, and I just want to say, this is already unperturbative. So there was a original BA paper which said that relaxation time or conductivity is non-perturbative. In a way, in retrospect, so that time it was, I'm not claiming it was trivial that time, but now it's actually a trivial result. We understand it. So, of course, if you want to expand it in powers of 1 over V or do self-consistent, I know, Born approximation, whatever, you'll get 0. Okay, but then we continued with this, and this is sort of, this is already unpublished, we'll probably post it soon. We thought, well, what happens if our bus is small? Then, of course, Fermi-Golden rule rate doesn't work. But then we should be able to construct LIOM, so local integral of motion coupled to sigma z. And it turns out, again, in the weak coupling limit, we can write an explicit construction. So it's the same limit when we can write Fermi-Golden rule rate. And it's an expansion in commutators. I'm not really going into details. Just ask me, or this will appear soon. It's a actually very easy to see result. So we basically try to perturbatively find tau z, which commutes with the Hamiltonian, and expand it in functions of 1 over v. And this is like this following expansion in commutators with well-defined coefficients. And then we can ask, what's the norm of this integral of motion? And it's very easy, again, to show that if H bus is sort of generic, in a sense ergodic, then this norm behaves like this. So it's sum over k, and then we have 1 over v power k. This is this exponential suppression. With each order, our next correction gets smaller and smaller. It's suppressed by, you know, v squared, v cubed, so it's here. But, oh, sorry, it's not k factorial. Oh, yeah, it's k factorial squared. Yeah, it's correct. So, but then we have this factorial growth. So this operator grows factorially. Basically, the reason is that each time this operator gets bigger and bigger by extra link, and more links are included in the next commutator. So there's extra factor of n appearing each time. And then we can ask, okay, when this stops converging? So this is an asymptotic series, but there is some order until which it converges. And it's interesting that we get exact same result as FGR. So basically, we see that when this construction breaks down, FGR takes over. So and essentially, we can even show that if you're in thermodynamic limit, you can stop at finite order and get best perturbative integral of motion. And the lifetime of this integral of motion is precisely FGR rate. So we found that FGR is a bit more generic. It's actually more interesting than I thought originally. It's not just what we learn in school, like first order perturbation. So it has really deep connections to many things. And actually, some people conjecture these results, or at least not this one, but related results related to operator growth and so on. And my final slide: what happens in multiple impurities? Well, actually, not much. So we have more impurities, and we again ask a spectral function, how we dump energy. Well, now we say, well, let's consider a sort of less ergodic model. We will freeze all impurities instead of this boundary one and introduce these weak links. So now we have the same problem. We need to dump large energy V into this link. But then initially, when V is not large, we can just dump it to this cluster. But once V gets bigger, actually this cluster is not enough. So we have to add another cluster. So we have to include this weak link at least once. If energy gets even bigger, then we have to add twice weak links. And that's exactly what's going on numerically. So if we look into the spectral function, it has exactly same form, omega log omega. So the blue line, what I showed before, like ergodic mass. And then if we now start adding these weak links, then after some frequency, we see a step, which is exactly 1 over b squared. Well, it's forming golden rule rate, so I need to square it. Then we continue for a while in a parallel manner, and then another, and so on. So basically, and there are no finite size effects because we are looking into frequency. So basically, on the operator, from the operator growth perspective, what happens is that in this construction, which I showed before, here, well, occasionally we will get some higher power of V. But this, of course, still cannot fight factorial. So what happens is that if we compute now Fermi golden rule rate and also construct this perturbative integrals of motion, we will see that this exponential in this omega log omega will be renormalized by inverse density of impurity. But it's at most factor of 2 in this model. So we will see, like, well, critical disorder will be a little bit less by a factor of 2 than for one impurity, but that's it. That's the maximal bound or minimal bound. All right. So yeah, I don't know. I think I ran out of time. So I left some slides about extra details like relation to spectral function, and there is the connections with glass physics. But I don't know, maybe I should finish now, and if there are questions, I can mention those things as well. So basically, to summarize, I told you that fidelity susceptibility is a sensitive probe of chaos. And it's actually much more sensitive, we found, than other measures. And it's even related to classical chaos in a way that there it's exponential sensitivity of trajectories, here exponential sensitivity of eigenstate. And actually this definition could be extended to classical systems, even there are no eigenstates, but we can, well, spectral function is well defined and we can express fidelity susceptibility as a spectral function. That's something which I hope to work on. So I hope we can connect quantum and classical chaos definitions in this way. So we have maximally chaotic buffer phase. So there is no direct transition from integrable to chaotic, at least generically, it never happens. Then we found that disordered systems are not really special in many respects. So I should say in any respect. So like, I don't know, I mean, of course, sometimes if you have extra symmetries, you have to be careful. But if the role of the disorder is to break the symmetry, then sure. But apart from that, it doesn't matter. So there are many other systems which have slow relaxation. Flocky systems, cars, Fermi pasta Ulam, and classical systems. And actually generic systems which are close to non-propagating, or people call classical limit. So if our parent model consists of commuting terms, like, you know, ZZ interactions or whatever, then the system has hard time. Actually, you see in any order perturbation theory, conductivity is 0, because in any order perturbation theory, you only connect to finite number of sites. So you have in all these models, you have non-perturbative transport, which is super slow, but nevertheless, generically, it's non-zero. And I hoped I convinced you, at least we convinced definitely ourselves, that localization is really unstable in thermodynamic limit. But there is like interesting phase. There is exponentially long time with sort of non-trivial glassy dynamics, with very slow logarithmic transport, and 1 over f noise appears from there, and there are non-perturbative regimes on this localized phase. So there is a lot of interesting and poorly understood physics. So in this sense, MBL is like a very interesting subject to be continued. But as I said, disorder is not really special. Okay, so I think I'll stop here. Thank you very much for your attention.
Thank you very much. Thank you. So I just moved to my laptop. Are there questions from the audience online? If you have a question, you can just unmute yourself or just write the question in the chat. I read it. Maybe, yes, Marco. Marco?
Yeah, I have a question. Hello, I am Anatoli. I'm trying to put my camera on if it works. Hello, hi, good to see you. Yeah, thanks for the talk. It was very nice. So one like two sort of questions. One, what is from your point of view? How do you, let's say, comment the work by Imbri? Would you say there is a sort of assumption that it was made that sort of doesn't describe the setting that we were thinking it would describe? And second, if you can comment about the avalanche picture. So I have the impression from your argument that you gave on Fermi-Golden rule and level spacing that somehow the new thing you're saying is that you're computing this rate in a non-perturbative way, while in the standard avalanche picture they don't do that. Is that correct? Can you comment on?
So first, Imbri, of course, the correct answer I don't really know. We tried, and not just we. I talked to many people. No one was able to reproduce his results and to confirm or disprove them. So I don't really know. But there are two things which I would say like a little bit worrying. That in this proof, he doesn't give you a bound. So he says that it's stable, but there is no number. Like I know in KM theory, there is a number. So we even don't know what to check, at least numerically. So in private conversation, he said that his estimate was this number was 8, but now for 8, it's clearly, it cannot be correct. Then more technically, there is indeed, there are, as far as I understood, there are more than one assumption there, but one at least he says explicitly is limited level attraction. But then we actually, in the paper with Dries, we found that in some point we could interpret numerics on this fidelity susceptibility as precisely level attraction, and we were just wondering what's going on. But then we realized that actually in any perturbation theory, what enters is the ratio of matrix element of energy denominator. So what happens is that not that level spacing gets smaller than it should be, but energy, matrix elements get exponentially big. This e power 2s phase is actually coming because of transfer of the spectral weight towards zero frequency. So in ETH systems, the spectral function at below tau-less energy is constant. And here diverges as 1 over omega some power. So it basically means that if you push omega to Heisenberg, you see exponentially large matrix elements. So this never is discussed in Imbri proof, but it's happening. And this was seen not only by us, but in earlier works by Maxime and Dima. So you just see it. Even in MBL phase, there are matrix elements at arbitrary small energies. So now you have to. And then the other thing, yeah, we thought a lot. It took us a year to figure out what's going with avalanche picture. And that's why we kind of started this perturbative construction. And perturbatively, you actually see that the correlation length keeps decreasing because of this factorial. So it's log V minus log K, 1 over log V minus log K. So, and then you can understand same criterion, where Fermi-Golden rule rate is equal to level spacing, where local integrals of motion stop working, as criterion where local differentiable correlation length diverges. So actually, they all postulate that there is exponential thing, but if you revisit numerics, I just looked into this paper by Maxime and Dima, you just see a curve which looks like this, and there is a straight line through it. It just curves very visibly. So I would say it's not very good numerical analysis. I'm sorry, I know, well, they're not here, they cannot respond, but still. What they had to do, I mean, it's up to 9L because they look into half of the system and system is 18. But even there, they had to extract this correlation length from sizes, I don't know, 3 to 7, then 4 to 8, then 5 to 9, right? And see whether it's the same. And on the picture, it visibly gets bigger. So, but our perturbative construction is rigorous. So what we are thinking now is, can we go beyond? If you do Borel resummation, you get infinity. So it's like different from you have alternating sign where you have convergent. But this infinity is only if you assume continuous thing, and if it's discrete, Borel summation doesn't help. So we are trying now variational approach and so on. But at least we can guarantee now that perturbatively this correlation length keeps increasing with system size. So it's like factorial versus exponent. Factorial wins.
Okay, thank you.
Other questions?
Yeah. So, so in the work you showed by theorem, so it looks to me that it was very crucial to be able to look into like L 200 sites, 100, 200 sites. I don't remember exactly. So could you indicate what? I mean, how they could be able to go to touch? So it was XXX plus boundary spin. So probably they used something specific to that model.
Yeah, I think you should ask them. But basically, this is some Krylov space method. So system size like plays very little role. So they built Hilbert space from commutators, and they said that they found some way to do it better than people were doing before. So that's all I can say. They guarantee it's exact. You see, it's finite time. Of course, you cannot do infinite time for these system sizes. This is like beyond exact diagonalization. But somehow, like before, they were actually, they were developing these methods in 2019. I forgot which times they reached, but they were improving, and they reached like incredible time. So it's probably I just invite them with the seminar and then ask for the methods. All I can say.
Okay, thanks.
Actually, Marco, you want to ask?
No.
Sorry. I just wanted to ask you if you can tell us a bit more about glassy dynamics. You didn't say much.
Oh, sure. I kind of ran out of time. So this part, which is not like really well understood. So let me. Can I take 5 minutes to answer your question?
Yes, sure. Yes, sure. Thanks.
Okay. So basically, then in this work with Dries, when we looked into fidelity susceptibility, we looked a little bit more into this number. Actually, what you can show from Hellman-Feynman theorem or whatever, that fidelity susceptibility is nothing but the integral of the spectral function divided by frequency squared. Of course, this integral is cut off at level spacing. Let me not go into these details. So, well, this is really easy to see. Because this is overlap of derivatives. When we do first order perturbation theory, you get energy denominator, you have two derivatives, you have energy denominator squared. And the stop is really like a spectral function. So basically the fact that the sensitivity of eigenstates is a probe of low frequency or long time behavior of the spectral function. That's why actually sensitivity comes from. And then we just see that roughly this integral, it diverges unless f vanishes. F squared. So we roughly can estimate it as f squared of the spectral function divided by Heisenberg frequency. And in ergodic systems, this is constant. I'm not taking into account some 1 over square root of L or whatever polynomial corrections, then irrelevant here. And this is really e power s. So that's where this exponential sensitivity comes from. And then what we found in this actually previous paper with Mahid, that in integrable systems, this integral, as I said, converges, fidelity susceptibility is not divergent. So it means that this spectral function should vanish at least linearly. And maximal chaos, we know e power to s means that the spectral function should diverge itself. And this is what I was answering Marco question. It should, this is matrix element squared, basically. So it should diverge as 1 over, well, matrix element doesn't diverge, but spectral function is matrix element times e to the minus s. Anyway, so relatively to ETH, matrix element diverges as 1 over. And this is indeed like what happens to XXZ model. So if it's integrable, we look into spectral function, there is diffusion or KPZ or whatever, which people found recently, and at relatively high frequencies. So in thermodynamic limit, this actually high frequency drifts to left. This is like tau-less frequency. Like for diffusion, it's 1 over L squared. But then in integrable systems, these spectral functions go down. And you have bigger system size, they're very small. But if you break integrability with some number, you actually get opposite. So in ETH, it would be constant. And here, it just exponentially increases. This is e power 2s. And you see it increases with the same time tau-less energy rapidly goes down, much faster than here. Good. So, and then we looked into what happens in MBL with Dries, or in this disordered regime. And we found interesting result, which we still don't understand. So this spectral function diverges as 1 over omega. Again, this is finite size numeric. So here we got a lot of critique and we switched to other explanations. We are not claiming it's 1 over omega. It could be anything. So, but it's something close to 1 over omega. Like for example, here, different lines are different disorders. So small disorder, it's 1 over square root of omega. I mean, if you fit this line here, it's perfect. It's really 1 over square root of omega. It's on the right panel, you just see. This is diffusion. So this is 1 over omega, and it fits reasonably well. So let's say it's something close to 1 over omega. But this is really also noise, right? It's symmetric correlation functions, 1 over f noise. And if you take Fourier transform of this 1 over omega, you will get log t. Fourier transform is 1 over omega is exactly log t. So we see that and right panel is actually the same as left panel, but now we fix disorder and increase system size. So it's one of these lines, I forgot which one, say this one, and then we increase system size, and you see, you kind of again approach 1 over omega beta and beta. So, and then from this we can extract tau-less time, which is precisely this, has this exponential thing. We just require that the integral of this is 1. And this basically logarithmic in time behavior, which is consistent with log spreading of entanglement entropy and so on. It had a very, very nice qualitative or empirical explanation by recent work by Mid-Murray collaborators. They basically said that we have sort of Griffiths, but not in real space. Actually, real space doesn't have huge fluctuations. It's actually in energy space. So, and because the same happens for quasi-periodic, even for one impurity, Dries checked, we still have the same 1 over omega. So basically what happens is that we are in this weakly ergodic regime. No, it's not even ergodic. So it's like intermediate regime, neither integrable nor non-integrable. And there, our different energies behave very differently. If the system is completely localized, they're completely different, right? Because they belong to different like spatial configurations and so on. But here we are sort of in between. And then they basically said, well, let's assume that we always have Fermi-Golden rule rate, but Fermi-Golden rule rate is a strong function of energy. And they were able to sort of explain empirically these curves. So, but one way or another, it's clear, by the way, from this work, it seems there is no variable subdiffusion exponent. It looks like we have 2 regimes, diffusion and this intermediate regime. Because it's log T, we can call it glassy. Whether it's real glass, whether we can, I don't know, do aging and so on, we simply don't know. So we need more. But the good thing that if you do classical models, you get exact same behavior. So once we take a standpoint that quantum mechanics and disorder are not that important, we can study like much bigger classical systems, and hopefully we can understand what's going on.
Okay, thank you. Are there other questions? Okay. Okay, no. So if not, thank you, Anatoli, again.
Oh, thank you very much, everyone.
Very nice seminar. Thank you.
Okay, bye, everyone.
Bye-bye.
Bye. Bye. Thank you.